Transportation engineering is the application of technology and scientific principles to the planning, functional design, operation, and management of facilities for any mode of transportation in order to provide for safe, rapid, comfortable, convenient, economical, and environmentally compatible movement of people and goods.
Take a guess.
This is a general intersection. These are the signal heads that display the lights. This is a loop detector that detects the presence of vehicles. And this is a cabinet where all the information is used for traffic timing.
The most important component of the signalized intersection is the cabinet. The cabinet holds everything the intersection needs to run smoothly. Within the cabinet is the traffic signal controller. This is the brain of the intersection. Modern controllers are capable of fully actuated operation, producing signal timings that vary depending on level of traffic demand. It uses settings that have been programmed inside it, along with vehicle demand for each phase as presented by vehicle detectors, to make decisions on the allocation of green time to various phases. It has 6 possible settings: basic settings, coordinated settings, time of the day settings, preemption settings, detector settings, and special settings. The conflict monitor, also known as the malfunction management unit, checks the operation of the traffic signal controller to make sure that an electrical glitch does not create a dangerous situation on the intersection. It has 3 basic functions. Number 1, to check for simultaneous activation of conflicting phases. Number 2, to check for absence of a red indication on a phase that does not have a green, a yellow, or a walk. Number 3, to check for insufficient operating voltage that is usually due to power interruption. Upon the detection of a malfunction, it immediately places the intersection into latched flashing operation, which basically means all lights flash red. The detector units identify vehicle actuations based on information sent to the unit by their associated field units, and they pass this information along to the controller for use in timing the intersection. Detector units are referred to as detector amplifiers when they are used with inductance loops. In addition to identifying vehicle actuations, the detector amplifiers also power the inductance loops, resonating them at a selected frequency. The load switches are essentially electrical gating devices that allow the controller logic, which operates in a 24-volt DC system, to direct the 120-volt AC current to the various signal heads. A load switch is required for each signal phase, pedestrian phase, and for the overlap used at an intersection.
Pavement-invasive detectors include inductive loops, magnetometer, and magnetic. They are all embedded in the road and involve magnetic field. Inductive loop is the most common detector technology used, as it's simply as a coil of wire embedded on the road surface. The end of the loops are wired to the lead-in cable from the pull box. It's connected to the terminal strip in the cabinet. A base frequency is established when there is no vehicle over the loop. When a large metal object such as a vehicle moves over the loop, the resonant frequency increases. Traffic light sensors constantly test the inductance of the loop in the road, and when the inductance arises, it knows that there is a car waiting. Magnometer measures changes in both the horizontal and vertical component of the Earth's magnetic field. Magnetometers are useful on bridges, decks, and viaducts where the steel support structure interferes with loop detectors, and loops can weaken the existing structure. The magnometer consists of small in-row probes, a leading cable, and an amplifier. The magnetic consists of a coil of wire with a highly permeable core. This can only detect vehicles moving faster than a certain minimum speed, and therefore cannot be used as a presence detector.
There are two types of controllers that are used for different traffic flow settings. One is semi-actuated and the second is full actuated. Semi-actuated controllers are used for major roads that have a constant flow of traffic throughout the day. Their main function is to prioritize traffic on bigger roads by controlling the light intervals of smaller roads. They receive information from detectors installed on the smaller roads so that they are able to give the right-of-way to vehicles on the smaller streets when necessary, while keeping minimal disruption to the flow on the larger street. The second type is the full actuated controller. This is used for roads that have fluctuating patterns in the volume of vehicles throughout the day, such as roads that experience heavy traffic during rush hour. This type of controller is the most preferred because of its accuracy and efficiency. The system requires detectors on every road in every direction, allowing it to have comprehensive traffic information. Based on this data, the system is able to prioritize the right-of-way as needed. Also, the controller will establish the cycle and green light time that is necessary in order to maintain the most efficient flow of traffic in the area.
The National Electrical Manufacturers Association, also known as NEMA, follows a generally accepted procedure for numbering the 8 standard vehicle phases of an intersection, a procedure commonly referred to as NEMA vehicle phasing. When NEMA vehicle phasing is in use, odd numbers are used to designate the left turn phases, while even numbers are used to designate the through phases. A maximum of 4 left turn phases and 4 through phases can be designated using NEMA phasing. Numbers 1 and 5 are used to designate the main street left turn phases, while numbers 2 and 6 are used to designate the main street through phases. Phases 1 and 6 are located on the same approach, while phases 2 and 5 are located on the opposite approach. Numbers 3 and 7 are used to designate the cross left turn phases, while numbers 4 and 8 are used to designate the cross street through phases. Phases 3 and 8 are located on the same approach, while phases 4 and 7 are located on the opposite approach. The first left turn leads the opposing through movement, while the opposing left turn lags the opposing through movement. Lead or lag operation can have important benefits for a system of signals that have been coordinated to provide smooth flow along the main street. When there are no vehicles at an intersection, a condition that often occurs late at night, the controller will rest in whatever phase or phases have recall active. The controller is set to rest in green in the recall phase. When vehicle demand is sensed on a conflicting phase, a controller that's resting in green will immediately service that phase. If 2 or more conflicting phases have recall active, then the controller will cycle between these phases. If there are no recalls, the controller will rest in green in the last phase that received service. When there are no vehicles at an intersection, the controller can be programmed for red rest operation, displaying the red indication to all approaches. The controller will provide an immediate green indication to the first phase where vehicle demand is sensed. After the demand is serviced, and assuming no other demand occurs, the intersection will return to red indications on all approaches. Red revert timing is used with red rest to ensure that unreasonably short red intervals do not occur.
The phasing, cabinet, detectors, and actuated controls all work together to produce a safe and efficient service at a signalized intersection. These intersections address highway operations for all users. They allow the shared use of road space by separating conflicting movements in time and allocating delay. However, in some cases, the dual objectives of mobility and safety conflict, and one element may need to be sacrificed to some degree to achieve improvements in the other. Overall, improvements in traffic continue to be one of the main objectives for transportation engineers.